Hello, and thank you for joining today's short video clip on continuous insulation. This series is sponsored by the Colorado Energy Office.
Hi, my name is Robbie Schwarz with Built Tank Inc., and thanks for joining me today. Today we want to talk about continuous insulation. We really want to talk about three things with regards to continuous insulation. We want to talk about whole wall R value. We want to talk about condensation potential. That's the moisture issues associated with it. And then we want to talk about the drying potential of these assemblies as well, where we're using continuous insulation. And ultimately, we want to talk about it because the codes are starting to ask in these climate zones, now starting in climate zone 3, that some level of continuous insulation be installed in the assembly unless you're going to trade that off. Before we go too much further, though, we need to talk about what types of materials are out there that can be used for continuous insulation. This is a mineral wool product, a rock wool type product that can be used for continuous insulation. And then we have foam type products here. This is an expanded polystyrene material that you can use. You can use extruded polystyrene and then polyisoisonarate in the right climates there. Now, the big issue with these difference in these products is basically the permeability there, but we'll come to that in a minute here. We want to begin talking about whole wall R value. Now, the whole wall R value, when I say that I'm building a house with R20 walls, we're really just talking about the cavity behind this here, the cavity insulation. That bat or that blown product that's in that cavity will give me an R value of 20, but that doesn't mean that this whole wall's R value is equal to 20. It means that just at that point inside the cavity, when I add in the framing and I do an area weighted U value calculation, it brings down the total wall R value substantially. The framing factor is what we're talking about. And wood has an R value of 1 per inch. Therefore, at each stud, I'm getting this additional energy loss from higher temperatures to lower temperatures, or higher concentrations of energy to lower concentrations of energy through that stud versus through the cavity there. So it takes my total wall R value from around R20 to about half that, 10, 11, 12, somewhere in that range is where the total wall R value is. But if I put continuous insulation in that cavity or over those studs on the outside, for example, then I'm going to increase the total wall R value because I've stopped a lot of that thermal bridging. I've increased the R value through that stud. Then I hit this sheathing material, this continuous insulation material, and I've reduced the ability for energy to move through that assembly. I've increased the R value of the whole assembly. Now, if we take in windows into account, our total wall R value drops even further, especially if we're not using some type of continuous insulation. So continuous insulation is a great way to increase the energy efficiency of the house and your total wall R value of the assembly. Now, the next thing we want to talk about is condensation and condensation risk. And the ability to overcome that risk is to use a continuous insulation. So condensation happens when moisture gets inside of our assemblies and that moisture hits a cold surface. So the first condensing surface is the coldest surface inside of this assembly, which is our exterior sheathing material. Now, I can stop condensation by two means. I can try to ensure that moisture isn't getting into the assembly, or I can raise the surface temperature of that first condensing surface there. So I stop moisture from getting into the assembly by using a vapor retarder. I happen to like class 3 vapor retarders because a lot of moisture doesn't move through the assembly by the process of diffusion. So a class 3 vapor retarder stops a lot of moisture from going in from this process of diffusion, moisture going directly through the pores of the material like drywall into the assembly, from higher concentrations to lower concentrations. And then we have water that's moving with air. Think of air like a freight train. It's moving cargo from point A to point B. That cargo in this case is moisture, energy, and pollutants that air is carrying. And air actually moves a significant larger amount of moisture than the process of diffusion. So we want to build our houses tight, and we want to have a good, appropriate vapor retarder for the assembly that we're building so that we can manage moisture movement and we can gain more control and predictability of the performance of that assembly there. But if moisture does get into that assembly and it travels all the way to the exterior sheathing in its vapor state, it's going to condense on that first surface. That dew point temperature is going to be low enough that we're going to have this state of water vapor change from its vapor form to its liquid form. And if I raise the surface temperature by putting continuous insulation on the outside, then I'm going to keep it in its vapor state, and I'm going to have the ability for that assembly to dry, which kind of gets us to our next point, the drying potential of the assembly. Now, the drying potential of the assembly is created by a couple things. One is, what is the permeability of all the materials that are creating that assembly, and which one has the least permeability, the ability for moisture to diffuse through that material, and how am I going to overcome it so that I have at least good drying potential in one of those directions. Now, a lot of the foam boards, especially the skin foam boards that has that plastic film on it, have really limited permeability. So I'm going to have to ensure that my drying potential is all to the inside. So I'm going to have to choose a Class 3 vapor retarder or one of these smart membranes, like CertainTeed's membrane, for example. Sega and others make some as well, that can stop moisture diffusion in one direction but allow that diffusion back out of the assembly in the other direction. Kind of like a Gore-Tex jacket has the ability to do that. So I want to ensure that I have drying potential at least in one direction, ideally in both directions. And then I want to put on some type of cladding on top of that assembly. And a lot of people worry about material management with regards to continuous insulation and how we're going to actually put that material onto the assembly, and then how we're going to put our cladding on top of the material as well. So the cladding is really taken care of. I really don't think that it's a big issue. You can go to the manufacturer instructions and their engineering tables, and you can get heavy claddings, you can get lighter cladding materials. All of them work with continuous insulation. You might have to put on batten strips. You might have to do some other things that you're not used to, using longer connections that penetrate at least an inch into the stud, those types of things, in order to get your cladding to adhere. But what we really want to promote is some type of drying behind it. So in this case, I have a vented rain screen, and moisture is able to move down this assembly behind my cladding material in its bulk format. So rain or snow or whatever type of bulk water is going to dry or drain down past my sheathing here. And then I have the ability to allow air to move there as well, which promotes additional drying of the assembly. So we've talked a little bit about the continuity of our exterior insulation to ensure that we have a good whole wall R-value performance. We want to make sure that we have raised the surface temperature of that first condensing surface, and then we want to ensure that we have great drying potential and we have an assembly that works and works well. So thanks so much for joining me today with our discussion on continuous insulation, and thanks to the Governor's Energy Office for sponsoring this video.
Thank you for listening. For more helpful trainings and resources, please visit the Code Adoption Toolkit through the link in the description below.